Hello everyone. So, now today we will consider the laminar film condensation on horizontal tube. So, in many applications, industrial application, you will find that the condensers are horizontal and over that there will be film flow. So, condensation will take place over the circular pipe, horizontal pipe, and those film will fall in downward direction due to gravity. So, in condenser used in power plant, so those are cooled using this technique. So, first we will consider only single horizontal tube, and similar to earlier analysis whatever we have done for film condensation on vertical plate, we will use here and we will find the Nusselt number. So, you can see if you consider a single horizontal tube. So, obviously, if the surface temperature is Tw and vapor temperature is Tsat and Tw is less than Tsat, obviously the condensation will take place on the surface of the tube, and those film due to gravity it will just travel in the downward direction. So, the assumptions whatever we made in earlier study we will use the same assumptions here, and the at the vapor liquid interface we will use no shear stress boundary condition. So, you can see in this particular case theta will measure from here, okay, and x is measured along the surface in this direction. So, at any point it is tangential direction, okay, and perpendicular to this surface we are measuring y. Okay. So, at any point if you draw the perpendicular direction, so that is your y and tangential direction is your x. So, at a angle theta we are taking one elemental volume, so that is your d theta. Okay. So, obviously, so this is your condensate. Okay. The surface temperature is Tw and vapor temperature is Tsat. Okay. So, in this particular case G is acting in this direction, okay, vertically downward direction, but when we consider the governing equation you can see this will have two components, one in the tangential direction, okay, and another in perpendicular direction. Okay. So, when we calculate the pressure gradient from the hydrostatic relation for the vapor, so this component x direction component of the gravity we have to take, because we are considering the governing equation in x direction. So, you can see that we can just left hand side in the momentum equation it will be 0, you have del p by del x plus mu L del 2 u by del y square plus rho L g sin theta. Okay. So, in this case if you see, if you consider the film here, okay, so this is your x direction gravity and this is your y direction gravity and this is your g acting. Okay. So, obviously, you can see this will be g sin theta because this is your theta and this will be your g cos theta. Okay. So, in the x momentum equation we have written rho L into g sin theta, okay, the x component of the gravity. So, here now you can write from the hydrostatic equation in the vapor del p by del x you can consider. Okay. So, del p by del x will be rho v into g into sin theta, similar way, okay, in the x direction we are considering. So, if you substitute it here you will get del 2 u by del y square is equal to minus g sin theta divided by mu L rho L minus rho v. So, if you integrate this equation with the boundary condition that at y is equal to 0 you have velocity 0 and at y is equal to delta you have shear stress 0. So, putting the boundary condition I am going to write the final expression of the velocity profile. So, velocity profile you will get it is the same expression as earlier case, except g is replaced with g sin theta. Okay. And next we want to calculate the mass flow rate. So, we have to integrate from 0 to y. Okay. So, mass flow rate per unit width. Okay. So, m dot will be just integral 0 to delta rho L u dy. Okay. So, if you put u expression here, finally you will get g sin theta rho L minus rho v delta cube by 3 mu L. And if you consider the energy equation, so you will get only del 2 T by del y square is equal to 0, and the temperature profile will remain same as the case of vertical plate. So, temperature profile you will get T sat minus T is equal to 1 minus y by delta into T sat minus T w. Okay. So, now we have calculated the velocity, mass flow rate and the temperature profile. Now, we need to calculate the film thickness, or we are interested to calculate the heat transfer coefficient. Okay. So, in this particular case you can see that although your mass flow rate is 0 at x equal to 0, that means at this particular case, okay, so your mass flow rate is 0, condensation is taking place. Okay. But at this place your delta is not 0. Okay. The film, there is a finite film thickness at theta is equal to 0. So, obviously we do not know that, but we know that their mass flow rate will be 0, because it is a symmetric line, because you can see in this particular case at the vertical line, okay, it is symmetry, because whatever way it will flow here, this way also it will flow. So, we know that due to symmetry at this line your mass flow rate will be 0. So, in earlier case we evaluated the film thickness, but here it is difficult to find the film thickness, because you do not know what is the thickness of delta at x equal to 0. Okay. So, hence we will use a separate route where we will find what is the mass flow rate. Okay. In this particular case, for simplicity we will neglect the subcooling effect. So, we will use just latent heat instead of modified latent heat. So, neglecting the effect of subcooling, the energy balance can be written as you can see the in the left hand side it will be q double prime w into area. So, what is area? So, if you consider this elemental volume, okay, so this is your d theta, okay, and in this direction this is your x and this is your delta, okay, this is your delta. So, q double prime w into dx, okay, will be just dm dot v into hfg. Okay. So, the sensible heat part we are not adding here, we are neglecting it, and from the mass balance you can show that dm dot v will be just dm dot by dx into dx. Now, you see that in this case, okay, so x will be just r into theta. So, that means dx is your r into d theta. Okay. So, if dx is equal to r into d theta, you put in these expressions. So, you will get q double prime w, Okay, so this is your KL del t by del y at y is equal to 0. If you evaluate it, you will get as KL T sat minus TW divided by delta. Okay. So, you can see this you will put KL T sat minus TW divided by delta dx is equal to dm dot v is dm dot by dx hfg into dx. Okay. So, this dx you cancel. So, you will get, so this dx now you write dx equal to r d theta, okay, and you take in the left hand side. So, you will get as hfg dm dot divided by r d theta is equal to KL T sat minus TW divided by delta. Okay. So, now we have already know that m dot is g sin theta into rho L minus rho v delta cube divided by 3 mu L. Okay. So, from here you can find what is delta. Okay. So, delta, because we have here term delta. So, this we have to replace in terms of m dot, so that we can integrate it. So, delta will be just 3 mu L divided by g sin theta rho L into rho L minus rho v to the power 1 by 3, because here delta cube was there. So, it will be just to the power 1 by 3 and m dot to the power 1 by 3. Okay. So, now you put this expression of delta in this equation. Okay. So, what you will get here, m dot 1 by 3 is there. Okay. So, if you rearrange it, you are going to get m dot 1 by 3 dm dot is equal to r k L T sat minus TW divided by HFG into g into rho L minus rho v divided by 3 mu L to the power 1 by 3. So, you can see that now it will be easier to integrate, because you know that at x equal to 0, okay, m dot is 0, because it is the symmetry line, and at x equal to L, that means at the theta is equal to pi. Okay, at theta is equal to pi, it will be total mass flow rate. Okay, so, m dot total, okay, because all will be integrated, okay, from theta is equal to 0 to pi. So, you will get the total mass flow rate at theta is equal to pi. It is for the one side. So, if you consider both sides, then it will be just 2 m dot. So, here m dot is the mass flow rate per unit width in 1/2, okay, but you can see it is due to symmetry. In the other side also you will get m dot. So, total mass flow rate at the bottom you will get 2 m dot total. Okay. So, integrating the above equation, between theta is equal to 0 and theta is equal to pi. Okay. So, what you will get? So, now at theta is equal to 0, we are telling that m dot is equal to 0 and theta is equal to pi, it is m dot total. So, this m dot total will just represent as m dot t. So, you can, if you integrate, you will get 3 by 4 m dot t by 4 by 3. So, m dot t is the total mass flow rate in one side. So, it will be just r k L T sat minus T w divided by h f g into g rho L. So, here it will be g sin theta. Okay. So, it will be g sin theta. Okay. So, it will be just g rho L minus rho v divided by 3 mu L to the power 1 by 3. So, you can see now this sin theta is sin theta to the power 1 by 3. So, that you have to integrate. So, it will be 0 to pi sin to the power 1 by 3 theta d theta. Okay. So, now you have to integrate this. So, this if you integrate you will get 0 to pi sin to the power 1 by 3 d theta as 2 0 to pi by 2 sin to the power 1 by 3 d theta. If you integrate it you will get as 1.2936. Okay. So, now if you put this value here and rearrange it, so you will get the total condensation rate for one side of the tube, okay, you will get as m dot t is equal to 1.923 into g rho L minus rho v r cube k L cube T sat minus T w cube divided by mu L h f g cube to the power 1 by 4. Okay. So, now we have calculated the total mass flow rate appearing at theta is equal to pi, means at the bottom, and in one side we have written m dot. So, if you consider both sides then it will be 2 m dot. So, now you use the energy balance. Okay. So, if you use the conservation of energy then you will be able to calculate the heat transfer coefficient. So, you can see that this already we have derived. Now, the average heat transfer coefficient for the entire tube both sides can be evaluated as, so 2 m dot T HFG. So, that is the total heat transfer rate is equal to your, this is your H bar into A into T sat minus T w, right, and what is the area? Area is twice pi r, that is the perimeter per unit width. So, into 1, okay. So, 2 pi r into 1. So, from here your average heat transfer coefficient you can calculate as m dot T HFG divided by pi r into T sat minus T w. Okay. So, now you see here m dot T expression is here. So, you substitute it here and rearrange. So, you if you rearrange and based on diameter if you define the average heat transfer coefficient, then you will get as 0.729 into HFG G into rho L minus rho B into K L cube divided by mu L T sat minus T w d to the power 1 by 4. So, now we can calculate the average Nusselt number. So, average Nusselt number will be H bar into D divided by K. Okay. So, now in this particular case we have defined the average Nusselt number based on diameter. So, if you put it and rearrange it, so you will get this expression. Okay. If you consider, so this is the average Nusselt number for a single horizontal tube, okay, based on the diameter of the tube. So, if you compare this equation with the expression for the vertical tube, you can see D is replaced with L, okay, L cube, and this coefficient will be different. Okay. That is the just change. Now, if you consider laminar film condensation on a sphere, okay, and if you do the similar analysis, you can get the average Nusselt number, okay, similar expression, only this constant is 0.826, okay, 0.826, and it is based on the diameter. Now, this average Nusselt number we have calculated for a single tube, but in industry you will get a different columns of tubes. Okay. So, in the power plant these are used. So, if you see for this single tube we have already considered, and this is the film falling vertically downward direction. If you have two horizontal tubes just one above the other, then this film whatever is coming out from the first tube, it will go to the second tube and it will just fall. Sometimes it will there will be no continuous film. So, you might get this type of phenomena. But now if we consider that these columns of horizontal tubes, and we will assume that you have a continuous film thickness like this. So, for this condition where you have a continuous film and it is falling one over the other. So, you can see here. So, it is falling to the next and so on. Okay. So, for this we need to calculate what will be the heat transfer coefficient and Nusselt number. So, you can see if we consider total n tubes in a single column. So, this is the first tube, okay, then second tube, third tube, then this is the nth tube. Okay. So, these are column of horizontal tubes. Now, you can see from here when the condensation is taking place, obviously due to symmetry mass flow rate will be 0, but when it will come and fall on the second, there is a some mass flow is coming from the tube 1. So, similarly tube 3 it will get whatever condensation happened in tube 1 and tube 2. Similarly, when you consider tube n, so some mass flow rate will come whatever is collected from the previous tubes. Okay. So, this analysis now do in this way. We have already calculated this total condensation rate for a single tube, okay, and if you write in terms of m dot t to the power 4 by 3 and rearrange it, you will get this expression. Now, let us apply the above expression to the nth tube in the vertical array. Now, the mass flow rate at theta is equal to 0 for the nth tube is the total mass flow rate from the n minus 1 tube denoted as m dot t, t for total, for the nth tube to the power 4 by 3 minus m dot t n minus 1 to the power 4 by 3 should be equal to b, okay, where b is represented with this expression. Okay. So, this is your b. Okay. So, what we are telling that whatever total mass flow rate is coming from the previous tube, okay, so that will be just at theta is equal to 0, it will fall to the nth tube. So, if you consider this is the nth tube, then in the nth tube whatever mass flow rate is there, so that will be just minus the previous n minus 1 tube whatever mass flow rate if you deduct. So, you are going to get a single tube whatever condensation is taking place. So, that is the total mass flow rate and that is your B. Okay. So, you are telling B is equal to this expression. Okay. Now, you see when you are considering tube 1, this mass flow rate is 0. So, when you are coming here, so you can see that m dot t 1 from the tube 1 whatever you are getting m dot t 1 to the power 4 by 3 is equal to b, okay, from this expression, okay, because n minus 1 is 0. Now, if you consider tube 2, so for tube 2 m t 2 4 by 3. So, at this place whatever mass flow is coming, it will be just b plus whatever mass flow rate came here. So, that is m dot t 1 to the power 4 by 3 plus b, and m t 1 to the power 4 by 3 is equal to b. So, it will be 2b. Okay. And similar way if you go and if you go to tube n, then you can write m dot t n to the power 4 by 3 is equal to this m dot t n minus 1 to the power 4 by 3 plus b, and this will be your n minus 1 b. So, total will be n b. So, you can see that m dot t n you can write is equal to n b to the power 3 by 4. So, n is the nth tube. Okay. So, you can write n b to the power 3 by 4, and where n is the number of tube and b is the this expression. Next, let us do the energy balance. Okay. So, you can see the average heat transfer coefficient for the tube bank we can calculate 2 into m dot t n. So, at the nth tube whatever this mass flow rate is collected, so that is in both sides. So, 2 m dot t n HFG will be H bar into area into T sat minus T W, right. So, this is the Newton's law of cooling. So, now what is your total area? So, now you have n number of tubes in a single column. So, for a single tube, what is the area? This is twice pi r into 1 per unit width. So, twice pi r into 1, that is your for area for single tube. Now, in a single column you have total number of tubes n. So, n into twice pi r. So, that we have written as the heat transfer area. So, from here your average heat transfer coefficient, just rearrange, you will get m dot T n HFG divided by, so n pi r, okay, T sat minus T w, and m dot T n already we have evaluated as n b to the power 3 by 4. So, this is the expression, and B expression if you know, so that B expression you just put it and you get the average heat transfer coefficient based on the diameter as 0.729 into HFG G rho L minus rho B K L cube divided by n mu L T sat minus T w into D to the power 1 by 4. Okay. So, now let us calculate the average Nusselt number. So, here average Nusselt number based on the diameter we will consider, but how many numbers of tubes are there? So, there are n number of tubes. So, it will be based on n d. So, you can write H bar n d divided by K L. So, now this is your H bar d. So, if you put this expression, then n if you take inside, so it will be n to the power 4, and in the denominator 1 n is there. So, it will be n cube. So, you can put it in d. So, it will be n d whole cube. Okay. So, you can see this is the expression for average Nusselt number for the entire column of tubes, okay, and the expression is similar to the single tube except d is replaced with n d. Okay. And you can show that your average heat transfer coefficient for the nth tube is equal to the average coefficient of the first tube into n to the power minus 1 by 4, because this is your for the nth tube, and if you put for a single tube whatever we have calculated, so that is the first tube. So, you can see this relation, and similarly for the Nusselt number also you can write the average Nusselt number d for the nth tube is the average Nusselt number based on the diameter for the first tube into n to the power 2 by n to the power 3 by 4. So, till now we considered the condensation outside the tube. Now, if the steam is condensing inside the tube when it is flowing through the tube, then your condensation will take place inside the tube and the condensate will fall due to gravity in the downward direction. So, if you see, condenser used for refrigeration and air conditioning systems generally involve vapor condensation inside horizontal tubes. Condition within the tube are complicated and depend strongly on the velocity of the vapor flowing through the tube. So, you can see this is your tube, inside this condensation will take place from the surface, but due to gravity condensate will come and come down. So, the film thickness obviously will increase in the downward direction, and this is the condensate pool, and the Reynolds number of the vapor at the inlet, I is for inlet, V for vapor. So, Reynolds number of the vapor at the inlet you can calculate as density of the vapor into mean velocity of the vapor, the diameter of the tube divided by the viscosity of the vapor. Okay. So, if it is less than 35,000, then scientist Chateau recommends that H bar d as 0.555 into H prime f g g rho L minus rho b K L to the power cube divided by mu L T sat minus T w into d to the power 1 by 4. Okay. And here obviously H prime f g is the modified latent heat is equal to H f g 1 plus 0.68 into Jacob number. So, all these study we assume that it is a laminar flow, but it may become turbulent flow if your length of the vertical plate is more. Okay. So, if you consider again the vertical plate and you see how the condensation is taking place at x equal to 0, you have film thickness 0, and gradually in the x direction it will fall and perpendicular direction is y and delta is the film thickness. Okay. So, film thickness gradually it will increase along the downward direction. It is seen that the up to Reynolds number 30. Okay. So, how the Reynolds number is defined? Reynolds number is defined based on the film thickness Re delta, okay, is equal to rho L hydraulic diameter divided by mu L. Okay. So, what is hydraulic diameter here? So, if it is a vertical plate, you can see here. So, the perimeter, okay, perimeter you can see that heat transfer where it is taking place. So, that is L. Okay. So, L into 1, and what is the flow cross sectional area? So, if this is the L, okay, this is your L, L is the width of the, so you can see the L is the width of the vertical plate, okay, and the perimeter if you see, so it will be L, okay, P it will be L at any cross section, and the flow area AC will be L into delta, because at a particular x if you see that thickness is delta, then cross sectional flow cross sectional area will be L into delta. So, DH will define as 4 into flow cross sectional area AC divided by perimeter. P is the perimeter of the heat transfer. So, you can see at this particular position if we consider, so this is your L, okay, this is your L and this is your perimeter. In this particular case this is your perimeter, and at this place your flow cross sectional area is L into delta. Okay. So, this is your L into delta. So, the heat transfer where it is taking place, so that is your perimeter, and this perimeter is in this particular case at any location you can see that is L. Okay. So, DH will be 4 AC by P. So, if you see here it will be 4 delta. If you consider condensation on a vertical cylinder, so P will be pi d at particular location, if you see it will be pi d, and flow cross sectional area is pi d into delta. So, DH will be just 4 delta, and if it is a horizontal tube, in this particular case P will be 2 L. So, if it is your L in both side if you consider, it will be 2 L, and flow cross sectional area will be L into delta, and both side it is 2 L into delta. So, hydraulic diameter will be 4 delta. So, Reynolds number we are defining now, this hydraulic diameter we are putting 4 delta, and if you see that your in place of mass flow rate if you write, so it will be rho L into delta. Okay. So, that will be your 4 m dot by mu L. So, this m dot we know this expression. So, if you put it here, you are going to get Reynolds number based on delta is equal to 4 g rho L into rho L minus rho B delta cube divided by 3 mu L square. Okay. So, Reynolds number is defined in this way. Now, if you see at x equal to 0, okay, at this point, what is the Reynolds number? Because delta is 0. So, obviously, Reynolds number will be 0. So, Reynolds number 0. So, it is seen that up to Reynolds number 30, okay, you will get a laminar and it is wave free. So, you can see this interface, okay, it is almost straight line. Okay. So, there is no waviness on the interface. If you see from Reynolds number 30 to 1800, you will get a laminar flow, but on the interface you will get some waviness. Okay. So, this is your laminar wavy region, and if it is greater, Reynolds number is greater than 1800, then it will be a turbulent flow. Okay. So, inside also you will see that chaotic motion is taking place. So, this is some, so you will get turbulent zone. So, based on this Reynolds number, if you find the Nusselt number, then just we will present what will be the Nusselt number in different regime. So, Nusselt number already we have calculated based on the length average. So, you can actually write in this way after rearranging h bar L nu L by G to the power 1 by 3 divided by KL. Okay. So, this expression we have not derived, but in some book you will get this expression, okay, and this you can write as 4 point, you will get as 1.47 into Reynolds number delta to the power minus 1 by 3, and this is valid for laminar zone, okay, wave free zone. So, Reynolds number for Reynolds number delta less than equal to 30. Okay. So, if your this temperature difference is unknown, T sat minus T w, then actually you can represent the Nusselt number in this way. Okay. So, you can see here temperature difference is not coming. Okay. So, that derivation you can do as a homework, and you can show that wave free laminar zone where Reynolds number is less than 30, you can use this average Nusselt number expression. Now, for laminar wavy zone, laminar wavy region, okay, in the range of 30 between the Reynolds number between 30 and 1800. Okay. So, this you can use as H bar L nu L square by G to the power 1 by 3 divided by K L as R E delta to the power divided by 1.08 R E delta to the power 1.22 minus 5.2. Okay. So, this is the correlation actually. Okay. So, it is proposed by the scientist Kutate-Ledge, and in turbulent zone you can get for Reynolds number delta higher than 1800. So, you will get Nusselt number based on L H bar L nu L square by G to the power 1 by 3 divided by K L. This you can write as Reynolds number delta divided by 8750 plus 58 Prandtl number L to the power minus 0.5 Reynolds number delta to the power 0.75 minus 253. Okay. So, you can see here in this expression Prandtl number is coming, okay, and this is valid for Prandtl number greater than equal to 1. Okay. So, in this expression for turbulent region you can see in the expression Prandtl number is coming, and this is valid for Prandtl number greater than equal to 1. Now, if you consider inclined plates, so you have a plate, okay, so your condensation will take place. So, you will get this is the condensate, okay, and if theta is measured from here. So, this is your T w, this is your T sat, okay, and this is your inclined plate, this is your condensate. So, you can see in this case only the gravity will be different, okay, because gravity is acting in the vertical downward direction, but the plate is inclined, okay, with the angle theta. So, you can put H inclined will be just H vertical, whatever we have derived, into cos theta to the power 1 by 4, and for it is valid for laminar zone, okay, laminar region, and theta for less than equal to 30 degrees, sorry, theta less than equal to 60 degree. So, this gives satisfactory results especially for theta less than equal to 60 degree. So, today we considered the laminar film condensation on a horizontal tube. So, we did the same analysis as we did for the vertical plate, except the gravity in the x direction we considered as g sin theta, because we considered the x in the tangential direction on the surface of the tube and y in the perpendicular direction, and from there we calculated the velocity distribution, mass flow rate and temperature distribution. Then we used the conservation of mass and conservation of energy. While using the conservation of energy, we evaluated the total mass flow rate at the bottom of the tube, because in this particular case delta is the film thickness at x equal to 0 is unknown, but due to symmetry at x equal to 0 m dot will be 0, the mass flow rate m dot will be 0 at x equal to 0. Hence, we evaluated the m dot total at the bottom of the tube, and from there we calculated the average heat transfer coefficient and average Nusselt number. Then we considered column of horizontal tubes. So, we considered n tubes, and for that case also we evaluated the average heat transfer coefficient and average Nusselt number. Then we considered the Reynolds number based on the film thickness delta, and depending on different regime, whether it is laminar region wave free or laminar region with waviness and turbulent region, we wrote the correlation for Nusselt number. And finally, if we considered the inclined plate, and in this particular case you know that the gravity in the flow direction will be g sin theta, and hence h, which is your local heat transfer coefficient, you can write as h for the vertical case into cos theta to the power 1 by 4, and generally it gives satisfactory results for theta less than equal to 60 degree and for laminar zone. Thank you.